Welcome to our session today. The title today would be Oops, It's JTAG's Fault, Journey to Unlocking Automotive-grade ICs. The presenters are Zhongjie Wu and Yuqiao Yang. Hi. So the takeaways of this session would be, first, we reverse engineered the JTAG communication protocol used by the SPC58 Automotive MCU and its debugger. Then we replicated the waveform using an FT4232HL dongle. When we connect the debugger normally, it does 2 rounds of authentication. By analyzing the protocol, we were able to bypass one of them immediately. Finally, we used voltage fault injection to connect to the JTAG interface and receive a successfully connected status code, despite not supplying the correct password. In other words, we bypassed the JTAG verification. GoGoByte. We are GoGoByte. We are a hacker-driven company who believes one cannot defend without knowing how to attack. We are founded in 2020 by a team of researchers and white hat hackers from top-notch security companies. We have experience both in blue team and in red team. We know how to attack and defend. Our team members have shared researchers at security conferences like DEF CON, Hack in the Box, and Black Hat. We have published books on automotive security, on hardware security, and on wireless security. We are also deeply engaging with security communities like ASRG, Google Hack, and DEF CON Group, because we think the contribution by hacker communities is very important. These are some of our team members. So why and how do we design our product? GoGoByte's team members have been helping many OEMs and suppliers to patch security vulnerabilities. During the process, we identified a few challenges that need to be addressed and come up with corresponding solutions. First of all, design flaws. Automotive cybersecurity problems, when they are discovered at operation phase, a lot of them are hard or expensive, even impossible to fix, because they are design flaws. They lack risk control and patch management capabilities. So we provide Defense Weaver to help the industry with secure by design. The second challenge is insecure implementation. Many vulnerabilities we found are not because there was no consideration during design phase. They were because insecure implementation by developers during development phase. It clearly showed the lack of comprehensive security test and validation capabilities. We provide the GoGoBark suite to help auto industry with security test and validation. The third challenge is slow and inefficient security response. We reported vulnerabilities to some vendors. It took some of them only 1 month to push over-the-air update to fix, but some others took a year or more without actionable plans to fix it. We provide the Threat Hound automotive threat intelligence platform to help identify threats in time. Finally, we provide the all-in-one cybersecurity platform for automotive, Threat Trace, to tackle these challenges. This will allow us to orchestrate the applications and personnel inside and outside. It is common industry consensus that we cannot eradicate cybersecurity vulnerabilities before operation phase because of the complexity of automotive systems. So the agility of security response is a key performance factor of a vendor's security capabilities. Now, JTAG is a debug protocol that is widely used, not only on commercial devices, but also on automotive devices. Let's say the SPC58 series automotive MCUs. JTAG security is obviously going to be an important issue. Chip manufacturers and users do not want the chips to be abused via JTAG. So here are some commonly employed security measures. A lot of automotive parts conceal the debug signal traces in inner layer of copper on the PCB, and they scatter the test pads instead of using a connector. But this is not good enough. With specialized tools like a JTAGulator, which, by the way, is open source hardware, an experienced person can easily identify the JTAG ports. Some vendors would choose to permanently disable the JTAG. However, some chips do not offer this functionality. Also, disabling JTAG altogether is probably not good for diagnostics. Once the product is out in the field, we cannot diagnose the products for further issues. Some chips, for example, the STM32 series MCU, they provide a separate readout protection feature, where a flash read via the debug port is disabled. However, this feature is also vendor dependent. Some other chips do not have the functionality. Also, if a determined hardware attacker can connect to the debug port, he can probably also find ways around those restrictions. So securing the debug port itself is usually done using password authentication, as in the case in SBC58 series, which we will discuss later on. In theory, the most secure method to prevent illegal debug access would be to use a challenge response schematic with an asymmetric cryptography. However, this is costly to implement by hardware, and we have not yet seen anyone actually doing this. In hardware security analysis, we usually need to concern physical attacks, such as side channel analysis and fault injection attacks. These are all effective physical attack methods that target semiconductor devices themselves, and both have been demonstrated as effective in recent years. For example, side channel analysis tries to exploit the information that is not revealed in regular communication channels, as in communication buses or GPIOs. Instead, we need to connect the information from side channels such as power consumption, processing time, and electromagnetic radiation. This type of analysis is usually used to steal confidential data such as encryption keys or other credentials inside the IC. On the screen here, I have attached a typical screenshot of the power consumption of an AES processor, and we can clearly identify the 20 rounds of operation here in the graph. An attacker can try to use this information to reconstruct the AES keys that is used by the engine. Fault injection, on the other hand, refers to the attack where the operation of a semiconductor device is physically disrupted. This can be done, for example, by pulling the supply rail voltage outside of the operating range, by injecting a strong electromagnetic pulse, by changing the input clock frequency that is outside of the specified operating range, or by pulling the reset line for a too short period than specified. All of the above methods can generate errors in the chip in different ways. The fault injection attacks physically corrupt the data being processed in the chip and can cause the chip to output unexpected results. This type of attack is usually used to break into secure boot environments. As we can see here, an example is the IBI hack of the Tesla, which has been presented on Black Hat a couple of years ago, in which the attackers used the voltage fault injection to break into the secure boot and unlock a paywall feature. The other example is a Starlink dish hack, which the investigators also used a fault injection method to bypass the secure boot and run their custom code on a Starlink dish. So what motivated us to do this research? Well, password protecting JTAG is a common security practice, but we would like to understand how it works. We would like to examine the process to see if it is actually secure, even against physical attacks. Well, not much research has gone into JTAG logs. When we looked for those online, the only information we could find was people using JTAG to introduce faults into existing chips, not by bypassing JTAG logs. So we would like to explore the SBC5 JTAG authentication process. We would like to examine the process for potential vulnerabilities and exploit those vulnerabilities.
Okay. During one of our penetration test projects on a customer's BCM, we identified an automotive microcontroller, namely the SPC58. We find that the JTAG interface was open, but we could not access it because we had to split a password. We find issue in the authentication process and successful bypassed the JTAG log. Due to NDA signed with the customers, we could not reveal the model of the chip and the device and the test. Instead, we bought a flash SPC5 development kit to demonstrate the Intel process. The development kit is the SPC5 EC80E born from ST, and it comes with the official JTAG debugger, the UDE STK. For the SPC5 series, this includes the software and the hardware for debugging. reading and flashing firmware. In the development kit, we can identify the debugging hardware on the top left corner in a red box. The SPC file stores the correct JTAG password in a one-time programmable OTP memory section, which can only be written once. In order to start analyzing the authentication process, we first had to set a known password in the MCU. So we did. In the UDE user interface, when attempting to connect to a locked SPC58 MCU, we need to provide a password for the JTAG log. Subsequently, the UDE debugging hardware will use the 256-bit password to authenticate by JTAG. The MCU then combines it with the password in the OTP memory. If they match, debugging exercise would be given. Otherwise, connection failure. Now we attempt to analyze the entire JTAG authentication process. We identified the JTAG connector and sniffed the 5 signals: TDI, TDO, TMS, TCK, and recite. Using a logic analyzer with the official toys is connecting with the MCU. But before we begin the analysis, we need to introduce the JTAG 1149.1 particle. As stated earlier, the state machine is open spec. In simple terms, the JTAG particle is a state machine that follows the a sequence of state change depending on the localing of TMS. The SPC file and MCU completely adheres to this particle, and understanding the state machine greatly helps us to understand the JTAG authentication process. The UI of the logic analyzer help us rebuild the JTAG states at different times, allowing us to compare them with the JTAG state machine to understand when the chip is receiving instructions and when it's exchanging data. Although we can determine when the chip is receiving instructions and when it is exchange data based on the public particle, what we really want to know is the meaning of each instructions. This tends to be private. We know that the shift IR is the state for instruction transfers, and we see 6-bit JTAG instructions, as well as 10-bit instructions. Among them, the 6-bit instructions are explained in the SPC file series official files. However, the 10-bit instructions are unknown, so we had to guess a little bit. We used the logical analyzer to capture the JTAG authentication process under 2 scenarios. Here we give a wrong password, and we see that the UDE debugger retries several times to connect. Here we give the correct password, and the UDE debugger proceeds straight to transferring data. We can see that no looping involved, unlike the last time. This difference in the JTAG authentication process would tell us what to look for in the waveform to know if password check passed or not. If we compare the 2 scenarios side by side, the difference is evident. Think of like a login prompt. You give the password, wait for a bit until the machine finishes comparing it. Then the machine either says yes or no. Now that we know what to look for, let's further isolate the critical section of the authentication process. We noticed that the recite line, which is active low, only goes high halfway through the authentication. Using this information, we could eliminated all JTAG activities before the racing edge highlighted in red circle here. Yes, because up until this point, the JTAG engine is held under reset and all the activities should not have mattered. In this process, the errors enclosed the red box are nearly the same. We will conduct a more detailed analysis of this similar process. Now we only know that the meaning of some of the 6-bit JTAG instructions taken from official files, but we don't know the meaning of the 10-bit JTAG instructions. However, let's give a try and analyze. First, UDE issues the 6-bit instruction hex 01, which we know is to ask for device ID. Then the SPC file returns the ID. Next, the UDE issues hex 7 to select the JTAG password register to start the JTAG authentication process. After that, UDE starts to transmit data to the SPC5. The data here is identical to the password we give in the UDE user interface, and it is sent in plain text. When UDE finished transmitting the password, the instruction hex 3F is issued to stack bypass register for data operations. Subsequently, the hex 2A instruction is issued to enable exercise to E200.2, and from then on, all the instructions are 10-bit. UDE is attempt to enable debug exercise to the chip to determine if the JTAG authentication has been successful. Now comes the critical part. If the first JTAG authentication is successful, the MCU returns a 10-bit value of hex 201. With subsequent successful authentications, the return value becomes hex 209. When the authentication fails, it returns 0. It's worth noting that after the first JTAG authentication is successful and returns hex 201, a series of operations are performed without the need for further JTAG challenges. After the hex 3 instruction, it will also return hex 209. After that, if another JTAG authentication is successful, it will directly return hex 209 after the hex 2A instructions. If it fails, it will return 0. We want to know exactly when the MCU is performing password compression. Since we know that the instruction hex 2A can ask for the result of a challenge, the password compression must happen before this point, since in the right line. According to the datasheet, the value in JTAG password will be further transformed after the racing edge of TCK in the update DR state, as shown in the red box in the figure, and then the JTAG password will be compared against the JTAG password in the SPC5 OTP memory. Therefore, the time for comparing the password should be after the racing edge of TCK in the update data state marked with red line. Additionally, we need to guess the method of password compression. It may be sequential or parallel. If this is sequential, we could attempt to brute force the password using a time-set channel attack. If it's parallel, we may use power set channel or fund injection to bypass the JTAG lock. We try to attack using both timing or power side channel method with no success. Finally, we decided to attempt a fund injection. To conduct a fund injection, it should be done within the interval marked on the figure. There are the start and end positions we find earlier. The aforementioned JTAG authentication process occurs twice. Therefore, the second authentication is redundant, which complicates fund injection attacks. In other words, if using the official UDE debugger for the JTAG authentication, an attack using fund injection would have to succeed twice in a row to successfully connect to JTAG, which is too difficult. This is bad news. However, don't lose heart. We will bypass the redundant authentication by simulating the JTAG's TDI, TMS, and TCK signals using an FTDI dongle, emulating the debugger that doesn't perform redundant checks.
So first, we need to modify the hardware such that our emulated debugger and the official UDE debugger pictured here can both control the JTAG port. We identified some jumper registers on the JTAG lines to the MCU, specifically the input lines TDI, TCK, TMS, and reset, and changed them to 910 ohm resistors, such that when we connect our emulated debugger, we take control of the JTAG. When we remove our debugger, the JTAG will be controlled by UDE. Ultimately, we chose the FTDI FT4232HL dongle, this green PCB here, for emulating the debugger because it supports a wide range of hardware protocols using its very versatile MPSSE engine. We used PyFTDI project to control the dongle, simulating the JTAG authentication process. But it is important that we strictly adhere to the JTAG protocol state machine to ensure proper communication with the chip. For example, if we want to issue an instruction, we will need to start with the idle state and then proceed one by one through the state machine to here, the shift IR state, where we can shift in our instruction. Ultimately, as seen in the figures here, we utilized the FTDI dongle to fully simulate the entire JTAG authentication process used by UDE, except for the redundant authentication here. This diagram illustrates the entire process of a JTAG challenge using an FTDI. When the first successful attempt returns hex 201 after hex 2A, and hex 209 here after hex 3. With this, we have successfully bypassed the redundant authentication. However, there is an obvious issue. The delays caused by Python, the host OS, and the USB stack makes the delay very inconsistent and large, such that a direct fault injection is impossible to align in time. We need to improve the simulation by using the synchronous bit bang mode of FTDI to transform the JTAG communication process into 5 parallel data streams, as seen in the code here. And we output them to the FTDI chip at a set frequency, such that the entire process is very consistent and very short. Now we can fine-tune the fault inject position in this process. To take this to another level, we tried using FPGA to push the JTAG interface to its absolute limit. We did it at over 50 megahertz, and we performed over 40,000 triggers per second. Unfortunately, even at this high speed, we were still unable to notice any differences in the time it takes to process. So this is probably not how the comparison works. We could not mount a timing side channel attack. Now that we know that the comparison is probably in parallel, the obvious next step would be voltage fault injection. So how we did it? We made a hardware modification. Based on the schematic here, the core power supply voltage as marked here is 1.2 volts, which is regulated by the SBC5 chip itself through an external BJT. So in theory, all we need to do is to pull this rail to the ground, temporarily shorting it such that the voltage falls out of spec. On the actual PCB, we identified the BJT responsible for regulation as marked here, and a large capacitor on the backside of the PCB, which measured 1.2 volts and which we soldered wires to short it off. The result is a voltage curve that looks like the red line here. The custom-made PCB is the injection hardware we made, which consists of a MOSFET driver circuit, the MOSFET itself, which is N-channel MOSFET, a very short and thick wire to short the capacitor to ground, and here we output a trigger voltage shown in green by our FTDI dongle to control the entire process. As a quick side note, after the fact, we also retried the attack using a commercial fault injection device from Open Security Research, or OSR. We achieved the same effects. After that, we began to fine-tune the delay, depth, and width of the pulse, ensuring that the pulse was not too large to cause system collapse, as in the chip doesn't work at all, nor too small to render the fault injection ineffective. We determined the success of the fault injection based on the return code from the processor, hex 209 or 0. Ultimately, after hundreds of thousands of injections, we used the voltage fault injection to bypass the JTAG lock challenge. After bypassing the lock, we continue to use the FTDI to simulate the rest of the JTAG connection as shown here. Then we could do whatever we can over the JTAG interface. But in the same time, we are uncertain about the stability of our injection because, after all, we have tried hundreds of thousands of times. So this probably requires further research on our part. So mitigations for chip vendors are to use IC design techniques that mitigate fault injection attacks, such as a brownout reset mechanism in which the chip would reset itself once it detects a voltage falling below some threshold. Also, we should require multiple successful verifications with random intervals, such that a fault injection cannot align correctly in time. For OEMs and other chip users, if possible, we should permanently disable the JTAG port in any production hardware, such that the port cannot be connected at all. Also, if the chip has flash read protection, we should use it. As seen here in the official documentations, both of these methods are available with the SPC58 chips. So we will outline briefly our responsible disclosure with ST over here. To highlight, the ST response states that the SPC58 product does not advertise to be physical attack resistant. Well, fair enough, so that's why we are here. We would like to thank the following entities for their generous support. Without their support, this research would not have been possible. Okay, and here are the speakers and contributors of our research. Thank you for watching our session today.